Hello everyone, welcome to my channel. A quiet question in a moving universe. Tonight, let's begin with a simple image. Imagine you're outside on a clear night. The air is still. The world is dark and soft around you. Above, the sky looks calm, fixed, distant, timeless. But the calm is an illusion of scale, because while you're standing still, the Earth is rotating. The Earth is orbiting the Sunday. The Sun is moving through the Milky Way. The Milky Way is drifting with its neighbors. And beyond all of that, beyond the familiar motions that feel like travel, there is a deeper, stranger motion that isn't about objects moving through space. It's about space itself changing. The universe is expanding. Not like a bomb exploding into emptiness. Not like matter rushing outward from a central point. The modern idea is quieter and in some ways more beautiful. The distances between faraway galaxies grow because the fabric of space stretches over time. If that sounds abstract, good. Abstract things can be gentle, like fog, like sleep, like the moment right before a dream becomes clear. So tonight we'll follow the evidence, step by step, like walking slowly along a shoreline. We'll see how we know the universe expands, what expansion really means, how gravity fits into the story, why expansion once slowed and later began to speed up, and what scientists mean when they say dark energy. And we'll be careful with the most tempting question of all. Why is the universe expanding? We'll answer it in the way science can answer honestly, calmly, and without pretending we know more than we do. The first clue light that arrives slightly stretched. The universe is mostly unreachable by touch, but it is reachable by light. Every galaxy is a lighthouse, in its own way, shining not as a single beam, but as the combined glow of billions of stars, plus clouds of gas and dust, and the faint heat of long history. When that light reaches us, it carries patterns, tiny, precise fingerprints made by atoms. Spectral fingerprints, the universe's barcode. Atoms absorb and emit light at specific wavelengths. Hydrogen has its set of lines. Oxygen has its set. Sodium has its set. Oxygen. These patterns are so reliable that we can identify elements in distant stars without ever visiting them. Now here's the key observation. When astronomers look at the spectral lines of distant galaxies, those lines are often shifted toward the red end of the spectrum. This is called redshift. Redshift, told gently. Red light has a longer wavelength than blue light. When the same spectral fingerprint appears at longer wavelengths than expected, it's as if the light has been stretched. And for much of the 20th century, the simplest way to interpret that stretching was the Doppler effect, like the change in pitch of a passing siren, but with light instead of sound. If a galaxy is moving away, its light appears redshifted. If it's moving toward us, its light appears blue shifted. That's true in many situations. But on cosmic scales, there's an even deeper interpretation, one that matters for our story. Light can be redshifted because space expands while the light is traveling. The light is not only coming from something that was far away, it is traveling through a distance that is quietly growing beneath it, like a road lengthening while you drive. The result is the same signature, stretched wavelengths. A long journey turns into a long, soft stretching, the pattern that changed everything: distance and recession. Redshift by itself is interesting, but the universe didn't reveal its secret with a single redshift. It revealed it with a pattern. Astronomers learned how to estimate the distances to galaxies. This was not easy, and it required careful methods using certain kinds of stars and supernovae as standard candles, objects whose true brightness can be inferred, allowing distance to be calculated from how faint they appear. Once distances could be estimated, a striking trend emerged. The farther a galaxy is, the larger its redshift tends to be. In other words, distant galaxies appear to be receding faster. This relationship is often summarized by what people call Hubble's law, a proportionality between recession speed and distance. But the most important meaning is not the equation. The meaning is the picture. Nearby galaxies have small redshifts. Very distant galaxies have large redshifts. The effect is widespread, not limited to one part of the sky. That last point matters a lot. If it were simply an explosion from a point in ordinary space, you might expect to find a special direction, a center, a preferred region. But what we see, broadly speaking, is that the universe looks similar in every direction on very large scales, which suggests something subtle. Expansion isn't things flying away from a center. It's space itself, changing everywhere. What expansion really means, the stretching of space. This is where the universe asks us to loosen our everyday intuition. In daily life, when we say something expands, we imagine it expanding into something else. A balloon expands into the surrounding air. A building expands into the space around it. With the universe, we don't necessarily have to imagine an outside. The simplest, most useful concept is this. Expansion is a change in the scale of distances within space. A careful mental picture. Dots on a stretching surface. Here's a classic analogy, gentle, not perfect, but helpful. Imagine a balloon with dots drawn on its surface. The surface is a two-dimensional world. The dots are galaxies. As the balloon inflates, the dots move farther apart, not because the dots are crawling, but because the surface between them stretches. No dot is the center on the surface. Every dot sees other dots receding. More distant dots recede faster because there is more surface between them, and more surface means more stretching. This is not meant to say the universe is literally a balloon or that it has to expand into a higher dimensional room. The analogy is only meant to convey two crucial ideas. There is no obvious central point of expansion within space. The expansion is a property of space itself. Why your body doesn't expand? A common worry is, if space is expanding, why don't atoms expand? Why don't people expand? Why doesn't the solar system expand? Because on small scales, other forces dominate. Atoms are held together by electromagnetic forces. Planets orbit because gravity binds them into stable systems. Galaxies and clusters are also bound by gravity. The expansion becomes noticeable mainly on intergalactic scales, where the average density is extremely low and the stretching tendency of the universe can accumulate over enormous distances. So expansion is real, but it is selective in where it shows up, because the universe is a layered system of competing influences. Gravity enters the story. A universe can't easily stay still. Now we step into the deeper physics. Still gently, Einstein's general relativity is our best-tested description of gravity on large scales. Its core idea can be said in a calm sentence: matter and energy shape space-time, and space-time tells matter how to move. When you apply general relativity to the universe as a whole, treating it as roughly uniform on very large scales, you do not naturally get a perfectly static universe. A static universe requires delicate balance. It's like trying to balance a pencil perfectly on its tip. Possible in principle, but unstable. The more natural solutions, without fine-tuning, are universes that expand or contract. And here's an important shift in perspective. Expansion is not necessarily a force pushing outward. It can simply be the universe doing what the geometry of space-time allows, and in many cases prefers given its contents and initial conditions. A slow cosmic timeline expansion with different moods. The universe has not expanded the same way at all times. Its expansion history changes depending on what dominates the energy budget. When radiation mattered most, in the very early universe, radiation, photons, and ultra-relativistic particles was far more influential than it is today. As the universe expands, photons spread out, lower number density, and their wavelengths stretch, lower energy per photon. So radiation energy density drops quickly as the universe grows. This is why radiation dominated early and then faded into the background of cosmic dynamics, when matter took the lead. Later, matter, both ordinary matter and dark matter, became dominant. Matter also thins out as the universe expands, but it does not lose energy per particle in the same way photons do. Its density declines more slowly than radiation's. During this era, gravity worked to slow the expansion and also to amplify small density variations, building structure. This is the era when the cosmic web formed filaments of galaxies, clusters, and vast voids. A universe can expand and still form structures because expansion stretches the large-scale canvas while gravity pulls matter into local clumps when something else began to dominate. Then comes the most mysterious part of the story. Observations indicate that, in the more recent universe, expansion is not merely continuing, it is accelerating, speeding up in a very specific cosmic sense. This suggests a component of the universe that acts unlike normal matter and radiation. We call it dark energy. The discovery of accelerated expansion distant explosions as mileposts. How do you measure whether expansion is accelerating or decelerating? You need a way to compare how far away something is and how much its light has been redshifted, and therefore what the universe's expansion was like when that light was emitted. In the late 1990s, teams of astronomers studied distant Type Ia supernovae. Type Ia supernovae are useful because they have a fairly consistent intrinsic brightness. They can be treated with careful corrections as standard candles. When astronomers observed very distant Type Ia supernovae, they found something surprising. The supernovae were dimmer than expected in a decelerating universe. Dimming, in this context, suggested they were farther away than predicted by a model where gravity from matter steadily slows expansion. The cleanest interpretation was, the universe's expansion has been accelerating in recent cosmic history. A second cosmic surprise. Not loud, not dramatic, just an elegant mismatch between prediction and data. And then a new piece added to the puzzle. Dark energy, a name for the unknown that fits the data. The phrase dark energy can sound like a substance in a sci-fi vial, but in science, it's often used more modestly. Dark energy is, at its heart, a label for an observed behavior. Something is causing the expansion of the universe to accelerate, and it behaves as if empty space has a kind of energy with negative pressure. That negative pressure phrase can feel slippery, so here's a softer way to hold it. Normal matter and radiation tend to slow expansion through gravity. Dark energy behaves, effectively, like something that makes the large-scale geometry of space-time stretch faster over time. The simplest model, the cosmological constant. The simplest form of dark energy is Einstein's cosmological constant, a constant energy density filling space uniformly, not thinning as the universe expands. If the cosmological constant is real in this sense, then the expansion eventually becomes dominated by this constant background, and acceleration continues. This simplest model fits current observations remarkably well. But this is important. The fit does not mean we fully understand the underlying physics. The big, honest problem. When physicists try to estimate the vacuum energy expected from quantum fields, naive calculations produce a value wildly different from what we infer from cosmology, off by an enormous factor. This mismatch is one of the deepest unsolved problems in theoretical physics. So the calm truth is, we measure acceleration. We model it successfully with a simple parameter. We do not yet know why it has the value it does. In science, that combination clear measurement, incomplete explanation, is a sign that we are standing at the edge of something important. So, why is the universe expanding? Now we return to the question you asked, the one that sounds simple and is famously deep. There are different layers of why. Let's separate them gently. Why, as in, what physical law allows it? General relativity allows space-time to evolve dynamically. When you apply it to a universe that is roughly uniform on large scales, expanding or contracting universes arise naturally. A perfectly static universe is not the generic outcome. It requires special conditions. So one answer is, the universe expands because the laws describing space-time permit and often favor dynamic geometry rather than a fixed, static space. Why, as in, what sets the expansion rate over time? The expansion rate depends on what the universe contains. Radiation dominated early, then faded. Matter dominated later, slowing expansion and building structure. Dark energy appears to dominate now, accelerating expansion. So another answer is, the universe expands the way it does because of the changing balance between radiation, matter, and dark energy. Why, as in, why these laws? Why these values? Why this universe? This is the deepest layer, and here science becomes careful. We can describe the behavior with extraordinary precision. We can test models against the cosmic microwave background, the distribution of galaxies, gravitational lensing, and supernova distances. But when you ask why dark energy exists at all, or why it has its particular strength, we do not yet have a complete, universally accepted answer. Sometimes why is not a single door, it's a hallway, and we're still walking. And that is not failure. That is how knowledge grows. First by measurement, then by pattern, then by theory, then by deeper questions that take longer to answer. A quiet detour. The Big Bang is not an explosion in space. At this point, a common mental picture tries to sneak in. The Big Bang as a bomb that exploded at a point and sent matter outward. That picture is understandable, but misleading. In modern cosmology, the Big Bang is best thought of as a hot, dense, early state of the universe everywhere. Not a point in space, but a moment in time. Space itself was smaller then, the universe was denser. As time passed, space expanded and the universe cooled. So, there is no special center of the expansion in space. Every observer, on average, sees distant galaxies receding. The Big Bang is a boundary in our past, not a location you could travel to. This is why the language of expanding space is so helpful. It gently corrects the explosion intuition. Horizons why we can't see everything, even if space is infinite. Even if the universe is extremely large, possibly infinite, we can only observe a portion of it because the universe has a finite age. Light travels at a finite speed, and expansion affects what light can reach us. The boundary of what we can observe is called the observable universe. It's not a physical wall. It's an information limit. Light from beyond that region simply hasn't had time to get here. And in an accelerating universe, something even stranger can happen over very long times. Some distant regions may become causally disconnected in the sense that their light emitted in the far future will never reach us because space between us grows too quickly. This can feel lonely if you imagine it emotionally. But it can also feel peaceful if you imagine it structurally. The universe has layers of access. It reveals itself in rings of time and distance, like a story told slowly, and we are reading the pages that have arrived so far. The evidence choir, many measurements, one expanding story. The strength of the expanding universe picture is not that it relies on a single observation, it's that multiple independent lines of evidence agree. The cosmic microwave background. There is a faint glow in every direction. The cosmic microwave background, the cooled remnant light from the early universe, released when the universe became transparent to photons. It is like a baby picture of the universe, ancient, soft, and incredibly informative. Its tiny temperature variations encode information about geometry, composition, and expansion history. Large-scale structure. Galaxies are not scattered randomly. They form a cosmic web. The statistical pattern of that web matches models of an expanding universe with dark matter shaping structure formation. Supernova distances. The supernova results provide a direct handle on the more recent expansion history, and they point toward acceleration. Gravitational lensing and clusters. The way gravity bends light and the way galaxy clusters grow and evolve also constrain the expansion and its components. These different methods, using different physical phenomena, converge on the same broad conclusion. The universe expands, and the expansion has a history that suggests dark energy dominates today. When the universe tells the same story through different instruments, scientists trust the story more. A calm summary: what we know, what we don't, and what it feels like to know it. Let's gather the main ideas. Gently, like folding a blanket. What we know well. Distant galaxies show redshift patterns consistent with expansion. The relationship between distance and redshift reveals a systematic, large-scale expansion. General relativity naturally allows an expanding universe. Multiple independent observations support a consistent expansion history. Evidence indicates the expansion is currently accelerating. What we don't fully know yet. The physical nature of dark energy. Why the cosmological constant, if it is the right model, has its observed value. Whether dark energy is truly constant or slowly evolving. Whether gravity behaves exactly as general relativity predicts on the very largest scales in every detail. And there's a quiet, comforting lesson here. We live in a universe that is not only vast, but also readable. It leaves clues. It allows measurement. It rewards patience. Even when the final why is still unknown, the path toward it is real. The universe expands, and you can rest. Now, return to the image we started with. A night sky that looks still, but isn't. A universe whose deepest motion is not a rush outward, but a slow stretching of space itself. Galaxies separated not by flight, but by growing distance. Light arriving to us slightly lengthened, slightly reddened, carrying news from long ago. Expansion is not a threat in the night. It's a feature of the cosmos, quiet, steady, unimaginably large. And in the middle of that expanding space, here you are on a small planet with a warm atmosphere, a thin protective sky, and a body that knows how to do one of the most ancient things life can do: rest. Let your thoughts drift outward the way space drifts outward, slowly, without effort. Let the question fade from sharp curiosity into soft wonder. The universe expands, and you can sleep.